Hey guys, today we're going to talk about L'Hopital's rule. L'Hopital was a French mathematician from the 1600s. He discovered something really cool. He discovered that anytime you're taking the limit of a function and you get an indeterminate form like 0 over 0 or infinity over infinity, if the function can be written as a rational function, meaning one function over another function, he realized that if you take the derivative of the top and derivative of the bottom and rewrite it, the limit of that is equal to the limit of the original function. Okay, so that's really useful in finding the limit of things that maybe we don't want to factor, or maybe things that don't even, that you can't find the limit any other way. So let's jump right to it. Here's a review problem. It's the old school limits like we used to do in the beginning of the year. How do you do this? You factor it, you cancel, and you take the limit of what's left. So when you plug in 2, obviously here you get 4 minus 4 is 0 over 2 minus 2 is 0. That's an indeterminate form, right? So what do? We do things. We factor it. When you factor it, these things canceled. Now you just have the x plus 2. Now when you plug in the 2, you get 4. And the graph will verify this. The limit of this function as x approaches 2 is 4. So now let's look at this one. Let's look at this exact same problem, but let's use L'Hopital's rule to find the limit. Here we go. So instead of factoring, I'm going to do exactly what I kind of said. L'Hopital's rule says take the derivative of the top and derivative of the bottom separately and rewrite them. All right, here's the problem. Derivative of the top, x squared minus 4 is just 2x. Derivative of the bottom, x minus 2 is just 1. So now let's look at that limit. The limit is x approaches 2 of this. Now I could just plug in 2. 2 times 2 is 4, divided by 1, you get 4, which confirms it's the exact same thing as when we did the limit using the factoring method. Okay, now be careful. One thing you do want to keep in mind, when you're using L'Hopital's rule, you are not taking the derivative of this function. The derivative of this thing is not this thing, okay? You're treating the top and bottom separately. Hopefully you realize the obvious reason that if you were to take the derivative of this, the way to do that is to use quotient rule. We are not taking the derivative of that. This is easier, okay? So remember, to do the derivative of that, you got to use quotient rule, but that's not what this is. L'Hopital is treating the numerator and denominator totally separately. Taking the derivative of each, rewriting it, and seeing then if you could plug in the limit. Okay, so right here, derivative of top and bottom separately. Here are some of the indeterminate forms that we might see in this class and in most calculus classes. The most common ones, you're going to see 0 over 0. You're going to see sometimes infinity over infinity. Keep in mind, when you have a number over 0, like I wrote 5 over 0 here and I crossed it out, that is not an indeterminate form. This just means usually the answer is going to be infinity, okay, or negative infinity. Here are some other indeterminate forms, but if you get some of these, you're going to have to change it to a fraction first if you want to use L'Hopital's rule. Feel free to pause at any point. Obviously, I'm kind of going fast. Pause and write the notes, whatever you need. Like I said, if any of these, you have to change to fractions first because look at L'Hopital's. It must be written as a numerator and a denominator in order to use it. Okay? So the gist of it is this. Copy this down. If you get 0 over 0 or infinity over infinity, you can differentiate the top and bottom, then take the limit. That answer will be your limit of the original function. Okay? Let's go to some practice problems. I've already done them. The shade is just over them, so I'm going to reveal it. So I'd like you, first let's talk about it. Let's try to plug in the limit straight up. If I try to evaluate this when I plug in 0, cosine of x is 1, so 1 minus 1, I get a 0 up top. Plug in 0 into this bad boy, I get 0 on the bottom, 0 over 0. I put a star here because that means I have an indeterminate form. I can use L'Hopital's rule. And that's what I want you to do right now. Because plugging 0 in straight up does not give us any information about the limit. And this one, look at it. I can't really factor it and cancel. There's nothing I could do there. There's no algebraic gymnastics I could do. So in this case, we kind of have to use L'Hopital's rule. So take the derivative of the top and bottom, then see if plugging in 0 works. Pause the video, give it a try, and come back when you're done. Okay, hopefully you've paused it, you've resumed it, and hopefully this is exactly what you have. Derivative of the top, 1 minus cosine x is sine of x. Derivative of the bottom, that polynomial right there, is obviously 1 plus 2x. Now let's try plugging in 0. Sine of 0 is 0. Plug in 0 into this, you get 1. And now 0 over 1. Don't think that's a weird form. That's just 0 divided by 1. The answer is 0. Okay? We could not get that using this form, so we had to use L'Hopital's rule to take the derivative of top and bottom to find the limit. Good. Number 3. The purpose of number 3, well, let's see as we go through. Plugging 0 in will get me 1 minus 1 is 0 minus 0. That's 0 in the numerator. Plugging 0 in the denominator gets me 0. 0 over 0. Star. Indeterminate form. I'm going to use L'Hopital's. Okay? So what I want you to do first is pause the video. Just do the first derivative of the top and bottom. Let's see if we get the same thing. Okay, hopefully you're back, and you have this. Remember, to take the derivative of this, you want to rewrite it as 1 plus x raised, quantity raised to the 1/2, because it's the square root. And then you use chain rule, bring it down, exponent drops by 1, and now you should chain the inside. The derivative of the inside is just 1, so I could have just write it times 1 there. I didn't, but I want you to know that the chain rule always applies. Don't forget that. The minus 1 went away when I took the derivative. X over 2, this is just 1/2 times x. So the derivative of that is just 1/2 right here. Oops, that's an eraser. Highlighter. There it is. Okay, that's the numerator differentiated. The denominator is obviously much easier. You get 2x. Now I'm going to try plugging in this 0, and let's see what happens. 0, that's 1. That's going to be 1 times a 1/2. You get 1/2 minus 1/2. That's a 0 in the denominator. Sorry, numerator. 2 times 0. That's a 0 in the denominator. Uh-oh. So L'Hopital's didn't really give me an answer, but I got another indeterminate form. The point of this problem is to show you that you can use L'Hopital's again. You can keep using L'Hopital's all day as long as you keep getting an indeterminate form. The goal is eventually we won't get one, we'll get an answer. So let's do it again. Take the thing I have highlighted right here, and now carefully take the derivative of the numerator and denominator of that. It's not that much harder than the first one. It's actually even easier. So try that, pause, and we'll come back and check. Okay, hopefully you took the derivative, and this is what you got. Same thing, using power rule and chain rule. The minus 1/2 goes away, it's gone. So you just have this in the numerator. Derivative of 2x is just 2. And now, let's try plugging in 0 here. 0, that's 1. 1 raised to anything is 1. You get negative 1/4 in the numerator. And 2 is just in the denominator. Look at that. That's not an indeterminate form. Those are two numbers being divided. So we divide them up, and we actually get an answer. Okay? Negative 1/8 is the limit. We were not able to do that initially. We couldn't even do that after taking the first derivative of top and bottom. We had to keep going and use L'Hopital twice. Okay, but eventually we got the answer. We know exactly how this function behaves at 0. It approaches negative 1/8. Excellent. Next up, 24, we have a multiple choice problem. Let's see. Oh, it's a limit problem. Cool, it's a limit, and I see a function over a function. So first I'm going to plug it in. Depending on what I get, I'm probably going to want to use L'Hopital's. Let's see. Plug in 3. Tangent of 0 is 0. And plugging in 0 in the denominator, e to the 0 is 1. Anything to the 0 is 1, so this is just 3 times 1. 3 minus, here the x is 3. 3 minus 3 is 0, so the denominator is 0. So clearly, oh, I got an indeterminate form. I'm going to want to use L'Hopital's rule. Here we go. I want you to pause, take the derivative of top and bottom, carefully come back and we'll check. Okay, welcome back. Hopefully you took the derivative of the top and bottom and you got this. Remember, derivative of tangent is secant squared. Remember, chain rule. That's why I wrote this times 1 here, even though I really didn't need to, because there's an inside function. It's x minus 3. The derivative just happens to be 1, so I wrote 1, but be careful. Chain rule always applies. That's why I wrote that as a reminder. Same thing with this 1 in the bottom. Chain rule. The inside is x minus 3. The derivative of that is 1. Derivative of e to anything is just e to that. Using chain rule times derivative of the inside, x turns into 1. Now I try plugging in 3. Secant squared of 0. Well, secant is inverse cosine. I know the cosine at 0 is 1, so the inverse of that is also 1. And if I square it, I'm still going to get 1. So I get 1 times 1. Numerator is 1. Denominator, plug in 3. Let's see, 3 minus 3 is 0. E to 0 is 1. 3 times 1 is 3. And then minus 1 is just 2. There you go. We actually got an answer. The answer is C, 1/2. Okay, so try the practice problems I posted. Try these problems. If there's any questions, please shoot me an email. I'll be available. Hopefully this helped, and I hope to talk to you guys soon. Bye.